Parallel? Perpendicular? Or what's the third option? Neither. And let's talk about how we can check this, like real easily. Like real easily. Just check to see if those two planes are parallel. Not nearly as much algebra as we just did in the last step. I mean, quickly identify this. I'll start with perpendicular. What do you think? Where are the normal vectors hidden in these planes? The coefficients. What's the normal vector of this plane? 1, 4, -3. What's the normal vector of this plane? -3, 6, 7. What would have to happen for those two planes to be perpendicular? You dot them, what would you get?
0.
Does everyone agree? So that's how we can check to see whether or not the planes are perpendicular. Take 1, 4, -3 as a vector. The -3, 6, 7 is a vector. Dot them, he says, if it comes out to be 0, those two planes are perpendicular. Right? You got this going on, or like this wall hitting this wall, the floor. Floor perpendicular to that wall, right? Aren't those two planes? Excellent. So we'll check that. But what if that's not true? How do you know if they're parallel?
They have the same components.
Yes! The corresponding components, all those ratios would be equal. So there's no way these are parallel. Look. Is 1/3 equal to 4/6
No.
equal? No. Yeah, I'll keep in mind the next one. This would have to hold true, and those ratios are not equal. By the way, you never care about that last number. That doesn't have to hold. These are not parallel, but that's what we do. I just say ratios, equivalent ratios, right? Are they perpendicular?
Calculate. They didn't calculate.
They are? And when she's saying yes, they are actually perpendicular. 1 times -3. 4 times 6, -3 times 7 is equal to what? These two planes are perpendicular. These two planes are perpendicular. If this didn't hold true and that didn't hold true, I would just say what? Neither. Neither. I have a problem like that in a practice set. It's number 25. Can we do something similar with lines? Right? Can we do something similar with lines? Let me come up with a couple. X equals Y equals Z equals 125 plus 4t, 5t, 6t. So I'm just making these up. Here's another line. X equals 17, Y equals 0, Z equals -2, plus 8t, plus 10t, plus 12t. Is there something we can approach similar with lines? Yes. So how do you know if the two lines are parallel? Right? Look at the vectors in front of these t's, right? The parallel vectors. Those would have to be, okay, scalar multiples of each other, which we mean is they'd all have to be in constant ratios, true? How would you know whether the lines are perpendicular? The dot product of that vector and that vector would have to be what?
0.
0, right? Well, that is not 0 because how could you have all positives dotted turn out to be 0? So they're not perpendicular, but are they parallel?
Yes.
Yes. 4 eighths is equal to 5 tenths is equal to 6 twelfths. These two lines are parallel to each other. Cool. And if neither of those hold true, it's neither. Cool. Hey, great. Hey, so you ready for 12.6? This stuff's really cool, everyone. We're now in section 12.6. We're talking about these quadric surfaces and cylinders. So we'll start with cylinders. You already know about planes, right? All right. Cylinders. This is 12.6. I'll take all this out. Let's start with cylinders. Oh, this stuff. This is interesting. This is an important section because throughout the whole course, Calc 3, lots of fun, but we're going to be seeing these surfaces all the time. And you're going to want to be able to just make a rough sketch. It does not have to be a perfect sketch, but just a rough sketch of stuff. So we're going to start with cylinders. The secret with cylinders, you know, they might have x squares in there and y squares and stuff. And here's an example. Z equals x squared plus 2. That's an equation of a cylinder. The secret is, how many variables are in this equation? That's what I want you to see. So for cylinders, you'll only see how many variables? Only 2 variables. Now I want to be careful, I can't say that's the definition, so I'm not reading a definition from the book, because didn't we just come up with an equation of a plane that had only 2 variables in it? But I'm talking about if you see 2 variables and it's got like x squared in there, or z squared and a y squared and stuff, then you're talking about some kind of what? Some kind of cylinder. Alright? It can even have a trig function. It can even have a trig function in there, but if there's only 2 variables, and it's not the plane, like we had before, where x and y, you just have 5x plus 2z equals 10. Then you're talking about a cylinder. So, what kind of cylinders are we talking about? They can be circular cylinders, or they can be parabolic cylinders. But the key with cylinders, you'll recognize them because they only have how many variables? 2. So I'm gonna hide this. Now, look at that relationship. Isn't that like a parabola? It's a parabola, but then it's shifted up what?
2 places.
2 notches. Which letter's missing? So what's that mean about y? It doesn't mean it's 0. Y takes on any value, everything. It's like y takes on everything in this relationship. So what we'll do is, when we draw this, just a rough sketch, I'll go like this. And when this is the x-axis, y-axis, z-axis. Z equals x squared plus 2. So think of y equals x squared plus 2. What did you do when it was y and x? You went up 2 notches on what? Y, and you went like this? So can you do that with me with the z-axis? Can you go up 2 notches? Right? But it's on which plane? Oh, it's on this xc plane, huh? So I mean, you want to distort it a little bit, you can. You can be like, all right, here it is. It's like right here. It hits this, and it's coming back up, right? It's going through this value 2 on the z-axis, right? In the xc plane, true? But I only drew 1 trace. I only drew 1 trace. We're saying y can be what? Anything. So can you ride down the road here since y can be anything? Come on down here, let's just draw a similar trace. How about right here? I'm going to try to like duplicate that. You go, hey, just be careful. I'm just trying to duplicate what I did in my notes right there on the green board. I'm like, okay, this came down here, and it came back up like that, right? And because y is anything, now draw lines that connect these. All right, here we go. And watch how my lines are parallel to which axis? The y-axis. Here, I can improve it now, right? Hey, what's this look like? Any descriptions? Anybody ride a skateboard or something like that? This looks like one of those skateboard ramps, right? Like the half-pipe stuff, the Winter Olympics. If you want to shade it in to make it look better, they call these rulings. If you want to make it look better, these rulings are always parallel to that letter that was missing. And there's the rulings. It's like a half-pipe. Cool. What kind of cylinder is this then? It's not a circular cylinder. It was like a parabola, so the adjective will be parabolic cylinder. Can you try one more of these? How about z? No. Yeah. How about z equals 1 minus y squared? You'll get stuff like that in our course. First of all, how do I know that's a cylinder? 2 variables.
2 variables.
Who's missing?
X.
X is missing. X can be
Anything.
anything. X can take on anything. We'll try to make a rough sketch. Ah, there's a 1 in front. It's shifted up 1. What did the minus do? Right? I'll do this in the z and y planar, and here's z, here's y. I'm going to go up here and just kind of what? Yeah. So far so good? This is the x-axis. Where can I make another trace? Somewhere down the x-axis, right? Because x takes on anything. Here, just make another trace. Here, you can always improve it, see? You just want to make sure that they're running parallel to the what? for that x-axis. Again, you can always put extra rulings in there if it helps. Shade it in. Just give it a little shade. There it is. Now it looks like a tunnel. True?
Mm-hmm.
There you go. So when you drive out tonight, you're going to be looking at shapes on the side of the roads going, it's kind of like the parabolic cylinder we did. No? Okay, great job with that. Well then what's this? X squared plus y squared equals 9, everyone,
There is circle.
in 3 space. So I want to make sure we're not just talking about 2 space, because in 2 space it's a circle.
Circle, yeah.
What's this?
Oh, sphere then.
And the key is, it's only got 2 variables.
Yeah.
So you know it's a cylinder. But this time it's not parabolic. What kind of cylinder is this? It's a circular cylinder, you bet. Because you're in 3 space, which variable is missing?
Z.
So that circle will be centered on which axis? The variable it's missing. That circular cylinder will be centered on the axis that is missing. Okay. What's the radius? I do want to point out, everyone, when I'm talking about this cylinder, you're like, is it all the points inside of it? No. It's only the points, when I'm doing this, only points on the surface of the cylinder is what I'm describing here. Okay? And I'll just run that down like that. This keeps going though, doesn't it? And if you want to go even further, this would be an infinitely long circular cylinder centered on the z-axis with a radius of what? 3. And it just keeps going. There's another trace. You can put traces all over the place. Keep putting traces. But the radius is 3, right? Centered on the z-axis is which letter was missing?
Z.
Right? So, you know, how about this guy? X squared plus z squared equals 4. Which axis is it on?
Y.
And it's a circular cylinder, right? You can just draw that y-axis and be like, here, here, there it goes. X, Z, there's X. But it's only the points on the what? That lateral surface. How do you describe points inside it? You just got to do a less than or equal to. Now you got all the points on the surface and inside. Cool. Great. So we did parabolic cylinders. We did circular cylinders. And, oh, one more. On my sheet here, I wrote this. Can you help me out with this? I wrote y squared plus 4z squared equals 4. That's got to be a cylinder. That's got to be a cylinder. It's only got 2 variables, right?
Mm-hmm.
But daggone it, it's not circular. But do you agree it's almost circular? So this stupid 4 being here, what did it really do to that nice, perfect circle? Stressed it. Like an oval? So they call this an elliptic cylinder. So it's going to look like this, right? Well, which letter's missing? If you wanted to make a rough sketch.
X.
So this is what I do. Never freak out about this. If you want to draw a rough sketch of this, so it's centered on the x-axis. I just use intercepts. You know what I mean? Like, pretend y is 0. And pretend x is 0. So x and y is 0. We're saying x can take on anything. What would z be? 1. What else could it be?
0.
Plus or minus 1. Do you all agree?
Uh-huh.
Let me make sure. If I let x and y equals 0 in this
Oh, yeah.
relationship, z would have to be plus or minus 1.
Uh-huh.
1. Well, let's pick another intercept. Ready? Let z equal 0. Let x equal 0. What would y be? Well,
Plus or minus -2.
plus or minus 2. So now you can see, if you're curious, which way is it more stretched? I just use intercepts. I just check the intercepts. Which way is this funny looking elliptical cylinder? It's an elliptical cylinder. Which way is it more stretched? It seems like it's more stretched along the what? The y-axis. Right, so now I'll go negative for y, right? This is the positive y. And for x, z, no. Yeah, plus or minus 2, the z went up what? 1, you can take this down 1. And here's one trace. Look at this. There's one trace that I got on my cylinder. One trace. But if you want to make another trace, which letter's missing?
X.
Go down the x-axis, duplicate that. Okay, here you go. Just duplicate it and then do what? Sometimes I have to improve it. I want to make this run nice and parallel. Just improve that trace. Or do you want to put some of these? They call these rulings. Make it look cool. You can. Elliptical cylinder. Elliptical cylinder. Hey, one more I want to show you before we do the quadric surfaces. They go just as quick, but it's so important we can do these. Now when this is in 12.6, I wonder if you could come up with this. Ready? Number 7. This one kind of stands out from the others. But isn't that a cylinder? Can I erase this? Everyone's equal sign y. How many variables?
2.
That's a cylinder. It's just not nice and circular. It's not a parabolic cylinder. The common ones we'll see, but we can sketch this, can't we? Who's missing?
X.
All right, well, let's just see. Let's get this thing started. Can we just do one trace of a sine curve? There's the z-axis. There's the y-axis. What's the sine curve do? You know, it goes up, then it what? It's like a pi value around here, then it comes back down and what? And they keep doing this. Right? And we keep doing that along the what?
Y.
The y-axis. Now which variable's missing?
X.
Let's make another trace. Go down here and just do what? Just duplicate this trace. Here you go. Now what is this really describing? I mean, it's a cylinder, but what is it? It's like a wave, isn't it? My bad. I meant to bring something. I was coming today. Here, then we'll just come back down like this. But I have some stuff that lies under my deck that runs the water away from the house. It looks just like this. And I bought it at Home Depot. It was real cheap. But it's amazing. Now it doesn't flood behind my house. I just gave it a slight slope, you know, directed away from the house. Water comes piling in here, gets on this thing underneath the deck, and just what? Runs along this stuff right outside. You know, right back down to the away from the house. But that, I just wanted to let you know, there's actual math equations that can represent. That's a cylinder. Let's do quadric surfaces. Quadric surfaces. Now, how many variables will we in quadric surfaces? 3. So we already know about a plane. What's a plane? Like 2x plus 3y plus 5z equals 8 or something, right? But the key about quadric surfaces, how many variables?
3.
3 variables. All right. Well, let's start out with the utmost, most important one. You'll see it often. But if you got all of them summed together, they all got squares, and then it just equals a number like, I don't know, 4 or something. Do you remember that from our first class? That's a sphere. Y'all recognize it? Where's it centered?
2.
That's a sphere, centered at the origin. What's the radius?
2.
2. So if you want to make a picture, feel free to just stick a little ball right here. Radius equals what? 2. Quadric surface. X squared, y squared, all, see, it's got 3 variables. Not a cylinder. It's a quadric surface. Cylinders are surfaces too, but we just call them cylinders. These are quadric surfaces. It's one type. Okay. But they'll have 3 variables in them. Alright, let's just talk about this then. 4x squared plus y squared plus z squared equals 4. Alright, that's close to that. What's that stupid 4 doing to it? It's not a perfect sphere anymore. It's stretching it. Alright, let's think of some words. I'll give you the proper textbook word. It's on that sheet. What, I think it's like a football, right? Okay, it's like I took some kind of what, sphere and just smushed it. Like a football, what, like a blimp? Like a blimp? And you go, well, what's the proper word? What do they call it? An ellipsoid. It's called an ellipsoid. A football, blimp, if you want to put other words down. The football, blimp, ellipsoid. I want to know which way it's more stretched though. You remember how to do this? You want to make a rough sketch? I use the intercept. What if x and y are 0? What's z?
Plus minus 2.
Boom! What if y and z are 0? I'll hide these.
Plus minus 1.
Good. So what he's doing is just plugging it in. And one more, what if these are 0s? I just use the intercept.
Plus
Minus 2. If you just wanted to see which way it's more elongated. Looks like it's stretched more along the x-axis. I mean, this is on the z-axis, right? And by the way, this is when I sketch these, you might just extend the z this way, and extend that a little bit more that way, and pull that more that way, where this was the y, and this was the x, this was the z, so you get the pluses and minuses. Plus or minus 2, boom, boom, psh, boom, boom, psh. More stretched that way, but here it's just like a 1 and a negative 1, and also on the y it went out too. And you can do one trace this way. You want to trace one through these this way. And they connect it. You know, it's not a perfect sphere, but it's what? It's just an ellipsoid. But it did get stretched more along this way, right? Along the z and the y-axis. It's more scrunched in at the x-axis. All right. Now, this is very important. I'm going to put both of these at the same time, okay? Z equals x squared plus y squared. Kind of erase that ellipsoid. Z squared equals x squared plus y squared. Okay, this is huge. Don't they look the same? Don't they look the same? They do. These two look the same. Can you imagine throughout our course how many times we're going to see that? How many times we see that? All the time. Now I want you to be able to look at it and go, gosh, I didn't memorize these. I think it's memorization. I think it's more conceptual. These are quadric surfaces, but they both look the same, don't they? Except this is missing the what? Square. So I think if you just fall back on your old algebra concepts, you'll know exactly what these two things look like. You know the quadric surfaces, right?
Mm-hmm.
So I'm going to hide that. I'm going to start here. Hide that. What does that look like? What kind of equation? To me, it looks like a parabola. Do you agree? Two-dimensional space, like z equals x squared, would be a parabola forming on the z and the xz plane, right? So what this becomes is, because that would just be what? Like a parabola?
Mm-hmm.
This is called a paraboloid. Alright. But then let's see how I did this, not by memorization, I just what? I hid this. I knew it wasn't a cylinder. But I said, oh, this is like a parabola, like y equals x squared, parabola, paraboloid. A paraboloid is like a windsock. This letter here is going to be the center, bless you. This will be the center of the paraboloid. So it's a windsock. So this, the variable that's isolated by itself outside the equal sign will be the center then. So when I'm going to sketch a nice paraboloid, what is it? It's like a windsock that just keeps opening up like this. So I'm just going to, and it's circular. Come up like this. I'll come up like this. But I'm just going to draw at least just one circle, one trace. I think one trace is good enough. And there's my parabolic cylinder. All these, like cross sections, would be circular. So it's really what kind of paraboloid? This was a circular paraboloid. Alright? Hey, what would make it an elliptic paraboloid? Elliptic, if it had like a 4 here and a 1 there, or a 9 there and a 1 there, then it would be more what? Like an elliptic paraboloid. Hey, what would this look like then, before I do this one? Z equal to 8 minus x squared minus y squared. What would that look like? You recognize it? You go, what is that? Oh, it's got all three variables. It's got the x squared and y squared, but z. So what did the minuses do? Took this thing, inverted it, but it shifted up what? 8 notches on the y-axis, and then it started fanning out like that. Does that make sense? Man, you're good. That's exactly what would happen. I mean, just a rough sketch. You're like, what's going on? It doesn't have to be perfect. 1, 2, 3, 4, 5, 6, 7, 8. And just let this thing kind of fan out like this, and you're like, that's what's happening. And we see things like this all the time. Okay, how about this? So let me hide this. It's look just like it, and I'm going to think about that in two-dimensional space. C squared equals x squared? Well, isn't that like if I square root both sides, what would I get?
It's equal to
It's equals x. And I'll put a plus minus in front because I took the what? Square root of both sides? Do you know what that would look like in two-dimensional space? If I square root both sides, I get this. Which means I got a line that goes like that, and I got a line that goes like that. You all agree? Once again, I don't do this by memorization, it's conceptual. I'm like, well, that's the relationship there. But now you go three-dimensional. You know what happens? In the circles form, guess what this turns into? What does this turn into? A cone. And you can call it a double cone. You want to call it a double cone because there's going to be two of them, right? So this will be a double cone, but we'll just write cone. It's a double cone. How do you know which axis it's centered on? The variable that's isolated outside the equal sign. That's how you know where it's centered. Right? So this would look like what? Circular cone, right? Because we can have elliptical cones. It's a double cone. Cool. Hey, later on in this course, you may see something like this, where the writer takes the square root of both sides. If I took the square root of both sides, I get what? And what would be in front? A plus or what? Minus. This is the top cone. And what would be the bottom cone? Just what? So most of the time you might only see this later in the course. But I want to let you know it just came from doing what? Square root of both sides. Hey, does anyone recognize the difference between a paraboloid and a cone? Cool. Hey, a couple more. Yeah, just a couple more. A quadric surfaces. What have we seen so far? The almighty ellipsoid, cone, and paraboloids, right? Well, now we have something called an ellipsoid. It's got all three variables. Oh, we did the ellipsoid. This is called a hyperboloid. Yeah. And I'll do it again. Both of these are hyperboloids. That's a hyperboloid. That's a hyperboloid. These kind of look like the spheres before, don't they? But what's new? First they have all three variables, right? What was different about these than with the cone? The cone was just x squared equal z squared plus y squared. There was no number in there. I see a number's involved now, right? But it still has all three what? Variables? But what's new about this, different from the sphere, is this has a what? A minus. So when you see a minus involved, you know this is what we call a hyperboloid. It has one minus. It's a hyperboloid of one sheet. Okay. How many minuses did this have? Subtraction signs. So you know what they call this? They call this a hyperboloid of two sheets. All right. Well,
Are these sheets the plane? Does the plane?
and we need other words to think about this. What I mean is something in real life. And I'm just going to hold this up. You're close enough. There's my pickup on there. What does that look like? It's like a nuclear power plant. Oh, and that's what hyperboloids of one sheets look like. Hyperboloids of one sheets look like, I'm saying nuclear power plant. All right, that's what they look like. Now, which axis will be centered on? Where the minus is in front. So, and see how this is the coefficient to what? The letter Z? So I'm going to draw something that looks like a nuclear power plant that's centered on which axis?
Z.
Z-axis. Look, circular here, it would bend in, but then bend back out. It's an open surface, so this would continue infinitely, right? In fact, of all the surfaces I've been doing, the only one that's a closed surface is the sphere of the ellipsoid. Everything else just kept what? Opening. And we're only talking about the surface. The cones did it, the paraboloids did it. This would do it. The only thing in terms of the word closed surface, you'd say the only thing closed up was the sphere or the ellipsoid. This would continue. By the way, you want to know what the radius would be right here in the plane? This is where the x-axis, the xy plane. Remember, for the xy plane, what would z equal? If you were just curious, what's the radius right there? You can see there's like an intersection right there in that little circle.
Half.
If you said z equals 0, what equation do you get? X squared plus y squared equals what?
1.
1. What's the radius of that little circle?
Half.
It's a radius of 1, isn't it?
No, that's the diameter. R square, right?
Yeah, but what
Oh,
we're saying
yeah,
is,
sorry, yeah.
do real, like if we said, hey, in the xy plane, z must equal 0.
Yeah.
So we're like, okay, hide that. Looks like you got the equation x squared plus y squared equals 1 right there.
Yeah.
It'd be a nice circle to raise 1. But then the radius just keeps what?
Right.
Getting bigger and bigger and bigger. Cool. Now let's come over here. This looks like, when it's hyperboloids at 2 sheets, it's like you get 2, almost like satellite dishes. Now, which axis is it centered on, though?
Z.
Over here, it was centered on where the minus was. In this scenario, it's centered where the 2 minuses aren't. It's where the positive is. Where's the positive?
X.
See it right there? So I'm going to draw 2 just satellite dishes. I'll come 1 unit off the origin right there. Just go like that. And then everyone, would you extend this x-axis and go negative? Because there's another one. Put it right here, just bend it off like that. And just put a circle. But these are, once again, open surfaces. They would just keep what? Opening up. Cool. Can you see there's a satellite dish? There's a satellite dish there, everyone. Cool. There's 2 of them. All right, there you go. Okay, again, how do you know which axis they're on? The what?
The one that is not,
The one that's positive. How do you know this was centered?
the one that is negative.
The one that was negative. Cool. Hey, there's one more surface. I never have you sketch it if you're curious. But it's called the hyperbolic parabola. All right, looks like a saddle. So I just want to put the equation right here. You don't have to sketch it, but it's called the hyperbolic paraboloid. All right, and what did the circular paraboloid look like? Z equals x squared plus y squared. What's the difference? See, it's not a cylinder. It's got all 3 variables, but what's between these? A minus. You don't have to sketch that ever by freehand, at least for me. But you can see what the image looks like in the book. And what does it look like? It looks like a saddle. Like the saddle actually on the back of like a horse or something. That just saddles, okay? You know, we'll talk about like later in this course saddle points. And right before you pack up, can I just blast like 5 or 6 images on the board and you just tell me what they'd all look like? Cool. We'll wrap up. Only take a second. I'll just write a bunch. Here they come. Well, how about? Let's see. We'll take that one. Oops. I need a different barrel. Okay, there's 2 of them. I need a few more. How about x squared minus y squared plus z squared equals 1? How about x squared equals y squared plus z squared? How about 9x squared plus y squared plus z squared equals 9? I'll throw this guy in a mix. Okay. Hey, we'll wrap up fast with this. You know, we can talk about it, and I can make a little sloppy sketch. We'll bolt out of here. Sound cool? All right. What do you think? Sphere. What's the radius? Radius. Centered where? Origin. So that's a sphere. That was easy. Come way down here. What do you think? Ellipsoid, right? And we can sketch it if we what? If we just go ahead. This is like the football, right? I'll just put the word. We can sketch if we had to, but we recognize that's ellipsoid. All 3 variables, all positive. You can see which way it's stretched. What's this? Yes. Of how many sheets? You go, what the heck does it look like? That's like a nuclear power plant, right? So this is like a nuclear power plant. Which axis is it centered on? The the y-axis. So I just go whoop, and whoop, and let it bend in and bend back out, and bend in and bend back out, right? Cool. These two look almost identical. Which one's the cone, which one's the paraboloid? Paraboloid? Circular paraboloid, which axis is it centered on? So I'm going to go to the y-axis, everyone. The positive y-axis, and just open up a windsock like this. Just put like, it's circular, it's a circular paraboloid. This is the cone, which axis is it centered on? X-axis, and here's the x-axis. I'll make it a double cone because it's a double cone, so I'll go, wow, wow, and it just comes out like that. You almost at like 45 degrees, wow, wow. And lastly, what's the story here? How many variables? 2 variables. This is a what? Cylinder. It's a circular cylinder centered on which axis? The y-axis. Me and you all are good. What's the radius too? Radius of 2. Have a great day! Super job, everyone.